Welcome, Geoff, please, and take it away.
I'm not sure I need this microphone, but thank you, Rene. That's great, and thank you all for coming. It's a lovely turnout, and hopefully what I have to say will be of interest to you all. It's really mainly focused around gold, because that's where the most recent advances have come. What the experts say about how you should work out how to sample gold has been a topic of great controversy over the years, and I think we now finally have it in terms of an easy way, or an easier way to do it, and a much more intuitive way. A little bit of background about myself. I started life as a chemical engineer in Canada and decided that if I wanted to do cutting edge stuff, I'd have to go to the States, and that didn't appeal to me. So I went into metallurgical engineering and worked on flotation for my master's degree. And as I was finishing that, I got an offer to go to Australia and do a PhD and do very, very practical work. I spent about 20 years in the coal industry, working on the modeling of various unit operations, from flotation up to jigs and Bradford breakers, and a whole bunch of stuff. And then got into ore texture analysis, which was aimed at trying to better understand how minerals break and how you create liberation of various mineral phases. I finished up working with the miners on rock mass characterization, developing methods for determining the properties of rock joint systems. And the very last one I did was looking at roof stresses in longwall coal mines, where they were using longwall mining. So I guess I've had a substantial experience in terms of different things. But the one thing that I learned very early on was that if I was going to do decent plant surveys, I had to learn how to take adequate samples in order to get precision on what I was trying to measure in terms of recovery and performance of these unit operations. And that's what got me into sampling, and that began in the 80s. And slowly but surely I began to do a bit of consulting in the area as well. And what you're going to hear tonight is really the distillation of all those almost 40 years of experience in the mineral industry, and in particular how we have managed to simplify the issues of gold sampling. So the talk has three parts. We're going to talk about, firstly, the sources of variance that you have to deal with in sampling, particularly a flow of ore from the pit or somewhere in the plant. And then we'll get into how a new theory of sampling can be constructed on a sound mathematical basis. Piaget, and in his work, when he developed sampling theory to the point at which it rested a year or so ago, he used heuristic arguments, and in fact he didn't finish the theory. He got so far as giving you the methodology for finding the sampling variance, but if we really want to complete the statistical theory of sampling, what we have to do is we have to determine the entire probability distribution for the potential samples that are taken under any set of circumstances. And of course, if we can make that calculation, we can in fact do a lot of optimization of the design of sampling systems. And that's really where my interest lies, in giving my clients optimized sampling systems that deliver a sample which is not just, as people say, representative, but is actually fit for purpose. One of the most important things in designing the sampling system is to sit down at the outset and decide how precise or how accurate you wish to be in terms of having a sampling system. I mean, why do you sample? You sample to get a result, but you're going to use that result for something, and whatever use you're going to put that to, there is going to be a consequence of inaccuracy. There's going to be a bonus from accuracy, better precision, if in fact you do the sampling properly. And the main issue is to get yourself a sampling system that is economically designed and is fit for the purpose to which you wish to put the samples. So what does representative mean? It's a word that's bandied around a whole hell of a lot, and it really means fit for purpose. So the big trick with sampling is to sit down at the outset, and this applies to exploration programs as well. Sit down at the outset and decide how accurate you wish to be. It's going to cost you money to be more accurate. You must make the trade-off between economic risk with loose numbers against less risk with accurate numbers. And because we understand sampling so well now, sampling systems can be designed to meet your real requirements so that your financial risk is in fact mitigated to an appropriate point. So my final bit of the talk is an example of gold sampling and how the new approach to gold sampling actually works. And it works well. So we'll get into it. The first component of sampling variance that you have to worry about is what we call distributional heterogeneity. This relates to the variation of grade as a function of time or tonnage as you draw material from your pit or from a feed stockpile or wherever you wish to start looking at your sampling. And the distributional heterogeneity, the variance that is associated with distributional heterogeneity, comes from the fact that the grade is varying as a function of time. And just like the geostatisticians, we model that variation using random function theory. That's the basis of geostatistics. We use the same basis for sampling and dealing with distributional heterogeneity. And if we can characterize the time variation in a statistical manner, we can then determine how frequently we must sample in order to achieve a particular precision. The next component of uncertainty that you have to deal with is what we call intrinsic heterogeneity. And indeed, this intrinsic heterogeneity comes from variation in grade and size between the particles in your broken ore. You really need to think of your broken ore as something that has been classified into size fractions, and then within each size fraction, you've classified it into composition fractions. And I've got an example here. This data came from a QuemScan, which is an automated scanning electron microscope. And we were looking for a phase called hazelwoodite. This is a converter matte example. When we're dealing with a coarse fraction around 2 millimeters in size, we have a reasonably narrow size distribution, a reasonably narrow composition distribution for our particles in that size fraction. If we look at a finer size fraction, we find that, and this is around 500 microns, we find that the composition distributions are spreading out. And in fact, the heterogeneity of that size fraction is increasing because the breadth of that distribution is increasing. We get down to a fine size fraction around 150 microns, and what's happened? Well, that center peak has disappeared, and now we have liberated phase of interest, and we have liberated gang. So the variance of this distribution gets large. If we want to quantify the intrinsic heterogeneity of an ore, what we need to do is evaluate a thing that's called the sampling constant. This thing has units of mass, typically expressed in grams, and it's given by this formula here, which, if you have your size analysis of your material and this kind of information on composition distribution, you can evaluate. The first term involves the amount of material, the mass fractions in different size fractions, and typical fragment volumes in that size fraction. The next term involves mass fractions of material in different composition fractions, a density term, and then a term in grade in a composition fraction minus the head grade for your material divided by the head grade, and that's squared. So this is a variance type term. It's influenced by the spread of that distribution. And most importantly, we can express the variance, the relative variance of our sample result as the quotient between the sampling constant and the mass of the sample that we collect. So as we collect more massive samples, our sampling variance goes down. As we collect smaller samples, the sampling variance will go up. And with this information characterizing the heterogeneity of our material, we can actually decide on reasonable sample masses to retain at various stages of preparation of our samples, and importantly, when you're sampling in the field, if you determine the sampling constant for your material at a coarse size, you can decide how much material you need to retain in order to control the relative variance. If that relative variance is too large, your numbers are going to get very sloppy. So it's extremely important to understand the intrinsic heterogeneity in your broken ore or your samples that have been crushed, and make sure that you're collecting a sufficiently massive sample to control the sampling variance. We can consider a whole automatic sampling system that is built into a tower somewhere in your ore flow. You've got primary ore coming in this case, minus 100 millimeter material. It gets sampled by a cross-stream cutter, and the increment is then crushed down to 10 mil, and again it goes into a hopper feeder so that we feed a secondary sampler in an appropriate manner, and those increments can be crushed again and go into a tertiary stage of sampling. And we can take away, at the end of a 10-hour day, in this particular case, we can take away 6 to 12 kilos of material. This is very handy. The lab guys can pick this up without any trouble. If we gave them a 50-kilo sample, they wouldn't be real happy. They tip half of it out on the ground, and boom, the integrity of our sample would be gone. Now, in sampling systems like this, and indeed all throughout the laboratory sample preparation stages, it is incredibly important to sample in what we call a mechanically correct manner. Sampling in a mechanically correct manner means that if we're taking a cross-stream sample at the end of a conveyor belt, our cutter must have nice parallel edges, and it must move at a constant speed. If it moves at a varying speed and there's segregation, lateral segregation on the belt, you're going to get a biased answer. And once you've biased a sample, there's nothing you can do. Sampling theory goes out the window, and you cannot get a handle on how accurate your sampling is. So you must, at all stages of sampling, sample in a mechanically correct manner. Your cutters must work properly, and the integrity of the sample that falls into the cutter must be maintained at all stages of sampling. And as I say, this goes right through into the laboratory, where in fact you shouldn't be using riffles, and you shouldn't be scooping some material out of a pile of material or a bucket. You must use rotary sample dividers. People don't use riffles properly. Use rotary sample dividers. They're easier. In fact, they're easier to use. And this should be maintained all the way down to the final analytical aliquot in the laboratory. People tend to ignore the fact that when you take, in the case of gold, 30 or 50 grams for a fire assay, they lump the variance that is associated with that 30 or 50 gram increment. They lump that in with the analysis variance, and that's not true. What you're dealing with is the intrinsic heterogeneity of the material that is submitted for fire assay. And the same is true if you're doing ICP analyses for base metals. If the heterogeneity, the intrinsic heterogeneity of your material is too high, that is, you haven't ground it fine enough or whatever, when you take the analytical aliquot away, you commit another sampling uncertainty. You bring in another sampling uncertainty, and it may be too large for you to tolerate. So, in order to design a total protocol, you need to know how your heterogeneity, your intrinsic heterogeneity varies as a function of top size of the material, all the way through your preparation process, and indeed, right down to extraction of the analytical aliquot. You should use a miniature rotary sample dividers. This little guy here is cheap. It's about, in Kiwi dollars, about $9,000, and easy to use, and it does the job properly. Really important, particularly for gold fire assays. So, the last component of uncertainty with which we have to deal is the actual analysis uncertainty. So this is separate from the uncertainty associated with your analytical aliquot. That uncertainty with the analytical aliquot is due to intrinsic heterogeneity. The analysis variance, if you're using an instrument like an ICP, that has to do with how well you've calibrated the machine and the inherent noise or drift in your instrument. In XRF, what kind of problems do you encounter? Well, you encounter matrix problems, and if you're using pressed pellets, you encounter particle size effects. Quite frankly, pressed pellets are really no good. You should be using fused samples. The problem is that you might put 10 grams into your little pot with your binder and press your pellet, but the X-rays that you're looking at are coming from the top, if you're lucky, 30 microns of your pellet. Particularly for, copper, 6.4 keV emission, it doesn't go very far in your material. So you're looking at not 10 grams, but you're probably looking at milligrams of sample instead of grams of sample. And this will have a much higher variance due to intrinsic heterogeneity, and it will blow your assays all over the place. So you need to use fused samples. Fire assays, there are a whole lot of issues there. Matrix effects, inappropriate fluxing for the material. And when you've got coarse gold, you can't break gold very easily. You can smear it in your puck mill, and that causes a bias, but it's very hard to break. It's very hard to break those gold particles because they hammer out and they turn into flakes. And if you've got coarse gold, you're going to have a problem with intrinsic heterogeneity of that 30 or 50 grams that you're putting into your crucible. And the only way around that is actually to revert to doing leaching of those samples. You don't have to grind as hard. And there's a rig in Australia, actually, from WA, which you can put a kilo of solids into each one of the pots in this machine. You can add some grinding medium. You can add your leach solution, and you tumble this thing for an hour, and you can do 52 pots at one time. And in fact, even if you start with 2 or 3 millimeter material, by the end of the hour it's down to 75 microns. So You analyze the solution that's left in the pot, you take the solids out, you wash them, you dry them, and do duplicate 50-gram fire assays on what's left, and you're going to get a good result. Much better than a fire assay on the original material. Another really big issue is in controlling laboratories is CRMs. Well, there's CRMs and there's CRMs, and not all of them are equally good. If they're too coarse, they're going to have a high intrinsic heterogeneity. They will segregate when you handle them, and you will get lousy results. You need to look into the CRMs that you use very, very, very carefully. Otherwise, your quality control in your laboratory is going to be all over the park. So, we've seen the three different kinds of variants that we can build up: distributional heterogeneity, intrinsic heterogeneity at all stages of our sampling system, and finally the analytical uncertainty. And fortunately, these uncertainties in statistical terms are all independent. And that allows us to simply add up the variances at each stage to get a total sampling variance. DH, IHs, and down to the analytical uncertainty. The fact that these are also independent random variables allows us to apply some very nice statistics to the problem and end up with a theory that doesn't stop at the sampling variance, but goes right through to allowing you to calculate the entire probability distribution for the potential results from your sampling procedure. And that, when you can do that, you then have a complete sampling theory. If you only stop at the variance as Pierre-Gilles did, you haven't completed the sampling theory. Come on. Okay, that's the outline of the variance sources that you can encounter. How do we then build a mathematical theory of sampling? Well, as I said before, you need to visualize your material in terms of the broken material being classed into size fractions, and then within each size fraction, your particles being classed into composition classes. And then we make a fundamental assumption about how particles arrive in correctly taken samples. And what we assume is that the number of particles of any one type that fall into a correctly taken sample follow a Poisson distribution. Now, a Poisson distribution is one that has a lot of variability in it, and indeed, it's really the only statistical distribution that we can consider for a basis of sampling theory. If we make this assumption, we can completely explain the variances due to intrinsic heterogeneity. The results come out to be exactly the same as what Pierre-Gilles put forward. So this is not upsetting the apple cart in any way whatsoever. It's just going past G's work and giving you a complete solution. So your sampling result is in fact what we call a random variable, just like the height of people in this room is a random variable. If we want to know in statistical or mathematical statistical terms, if we want to know everything about a random variable, we need to know its probability density function. And once we've got that, we know everything. Nothing more to know. And in fact, we can get there now. So there's a little bit of mathematical statistics, which says that if we have, for example, a weighted sum of Poisson random variables, and that comes from numbers of particles falling into a sample, there's a very powerful theorem in mathematical statistics which says that we can calculate a thing called a characteristic function for those random variables. and if you have a bunch of independent random variables, the characteristic function of the sum of those is equal to the product of their characteristic functions. So bang, we can go and we can write down the characteristic function, and then we can invert that and get our probability density function. It so happens that the characteristic function and the density function are Fourier transform pairs, which allows us to do the calculations that we need to do. Calculations are a little bit involved, but nothing beyond your laptop capability. So if we want to go and deal with distributional heterogeneity in addition to the variances due to intrinsic heterogeneity, we can, using the same characteristic function theory, we can in fact include that. We can combine that with the variance due to intrinsic heterogeneity, and we can combine it with the variance due to analytical processes. Even when we run into non-Gaussian or non-normal distributions, we can use this method, and that allows us to, for any circumstance, it allows us to come down to a final distribution of potential results from your sampling system. And it can be done as a function of grade or whatever. So we now have extremely powerful tools that we can bring to bear against the problems of sampling system design, as long as we characterize the material with which we're dealing. If you don't characterize your material, you know nothing. It's just a bucket of dirt. And you really don't know how to sample it. You've got to characterize it. And particularly in the exploration, at the exploration level, the sooner you characterize the material with which you're dealing, the better. Because you can then design your sampling protocols for exploration, and those will go through into the design of sampling protocols when you're actually in production and you're dealing with samples in the plant. So the sooner the better is the magic word in terms of design of sampling systems and solving your sampling systems in a manner that is fit for your purposes. When we want to look at analytical uncertainties, we can, with the exception of fire assays, we can determine these distributions by making replicate determinations. In the case of ICP, of course, we can use standard solutions, and we can determine what the calibration for the machine should be, and through that we can calculate the analytical uncertainties from our replicates. When you're dealing with instrumental analyses, your distributions are likely to be normally distributed or Gaussian, unless you're working near the detection limit for that particular element on that particular instrument. And indeed, if you're trying to work near the detection limit, you should find a solution to that. You either get a better instrument or a different method. Working near the detection limit is a recipe for disaster. So don't do it, and then you will be able to characterize your analytical uncertainties. As I've said, the final distribution of all sources of uncertainty is determined by adding up, using the characteristic functions for all the sources of uncertainty. And net result of this is a characterization of the total distribution of uncertainty for your entire sampling protocol, starting with your original ore. The sampling of gold is actually a very special case in sampling, and it's one that has caused people grief for 20 or 30 or 40 years. In fact, ever since Geoff started talking about his simplified formula for sampling, the business of figuring out how to sample gold has caused a lot of grief. And I'll explain why that is. And the problem is that if we look at the sampling constant, which is the number that we want to find so that we can determine correct masses and so on. The sampling constant in Pierre-G's simplified form involves a number C, which is a composition factor, which is easy to get. It involves a particle shape factor, F, which is reasonably easy to get. It involves a value G, which is a size distribution factor, which is quite easy to get. It varies between 0.25 and 1, so it doesn't have a huge influence. The real bugger is this liberation factor, L. And people have tried very hard to model L as a function of the 95% passing size of the ore. And this is the big mistake. We should not be talking about the ore. Consider two buckets of ore. One is coarse and one is fine. It's the same ore. The number of gold particles, unless we've ground the material in the fine bucket so far that we've totally and absolutely turned it to bug dust and liberated all the gold or smeared it or hammered it out or whatever, the number of gold particles in both buckets is very much the same. The size distribution of the gold particles in both buckets is very much the same. So if we know the size distribution of the gold, we know something very valuable about our ore. And it doesn't matter whether the material is liberated or not. The numbers of particles of gold clusters or grains of any one size or mass are the things that is what's controlling our sampling variance, and those numbers are Poisson distributed, and both those samples are very similar in terms of the sampling variance that we will incur. So, particularly a guy called Dominique Francois Bongarçon has been laboring this business of finding a formula for L as a function of top size. He's absolutely wrong. He is barking up the wrong tree. It just doesn't work. What you need to do is focus your attention on the size distribution of the gold, be it clusters or be it discrete grains. And you can show that under the circumstances where you've got low grade, where your grade is around in grams per ton, you can show that the sampling constant can be given by this function here. Density of the gold particles, or electrum if that's what you've got, divided by the grade, times the shape factor, times the size distribution factor, but now times the 95% passing size of the gold, not the ore. And this works really, really well. And I'll show you now why it works really well. A guy over in South Africa, a guy called Dick Minute, did some really nice work. And he took a gold ore, no doubt from Witwatersrand, and he divided a large sample into 4 nominally identical subsamples. The first sample he crushed to a 25 millimeter top size. The next one he crushed to a 3 millimeter top size. The next one he crushed to a 1 millimeter top size. And the last one he crushed to a 0.5 millimeter top size. And he used 273 grams for each of 30 samples, and he assayed them to extinction, fire assayed them to extinction. And these are the numbers that he got. For set 1, 15, 16 to 30. So for each one of these size fractions, we can actually calculate the variance of those results. That's the sigma squared value, the variance. Now we know that from that previous formula that the sampling constant is given by this expression, but we also know that Ks is equal to the mass of the sample with which you're dealing times the variance divided by the grade squared. So we combine those two and we can calculate the 95% passing size of our gold, be it effectively due to clusters, or be it discrete grains. So we know the sample mass, that's 273 grams. We know this from our data set. We know this, we know the grade, and we can have a good punt at the shape factor and the size distribution factor. So what I did was I took his data, I used F equals 0.5 and G equals 0.25. The average grade of everything like that is very close to 13 ppm, or grams per ton. This, I assumed it was gold, so it was density of 19. I know this number, I know this number, I calculate that. What did I find? I found that if I plotted the estimated top size of the material against, the estimated top size of the gold against the sample top size, the ore top size, I got this nice relationship. One of his students, a guy, Connie Spangenberg, some of you may know him. He's just retired from Anglo Gold in South Africa. He did a master's degree and he used the same ore. I used his results here as well, so they fell on the same line. That said they were the same ore. And the most important thing is that I was able to calculate this D95 for the three different top sizes. In the first case, I got 600 grams, 200 grams, 132, and about 94 microns for the sizes of the gold. And what's happening, of course, is that as we crush, we're breaking up some of these clusters and progressively reducing the effective top size of the gold. Okay, what can we do with this? We can, in fact, make two kinds of comparison. For the size distribution of the gold, we assume that it follows a Rosen-Rambler distribution, and that allows us to calculate for a given value of G, the size distribution factor, we can, in fact, calculate the entire size distribution for the gold. We can then use the characteristic function theory that I developed, and we can use that to calculate probability distributions or potential sampling distributions for the materials at the different top sizes. So we can calculate from either theory or the actual data, we can calculate sampling constants. And so for the top material, top size, we had a comparison between 39 and 44. Next size, 1.5 versus 1.48, 4.2 versus 4.1, 1.6 versus 1.6 basically. The grades were very similar. Relative standard deviations, of course, follow from this, and they're very similar. But most importantly, we can calculate on the basis that we were dealing with 30 samples, we can calculate the minimum to maximum observed grades. And we can use the distributions that we calculate to relate a 30 sample subset to minimum and maximum, basically confidence intervals at a particular level of confidence. And for the coarse material, 5.4 to 29 versus 4.3 to 27, 10.9 to 15.7, 10.9 to 14.9, 11.4 to 14.4, basically 12 to 14.1, and 11.1 to 14, 11.8 to 13.05. These agree very nicely. So not only are we seeing that the sampling constant and the relative standard deviations are agreeing between theory and actual data, but we see that the spreads of the distribution, the spreads of the assays that we got off these materials are actually agreeing. So the theory says that this is the distribution for the 25 millimeter material. So it's going from somewhere around 3 up to 30 odd grams per ton. The next size, it's going from a little past 10 up to 15 and a bit. Next one, it's going from a little past 11.5 up to, say, just under 14.5. And for the finest fraction, it's going from, let's say, 11.7 to about 13.1 or 2. So, this example demonstrates that if you get information on the size distribution of your gold, you can actually predict what your sampling distributions are going to be like. And this, in terms of designing your sampling protocols for a gold ore, is absolutely, completely invaluable information. It allows you to understand why you get tails on your distribution, and it allows you to do quantitative calculations in terms of sampling uncertainties. So, the new theory works. And it basically completes G's theory, and we now have a new tool that's actually relatively easy to use for characterizing gold ores, or any ore where we have a particular mineral phase that is present in low concentration and is our target mineral phase. All we need to know is the size distribution of the clusters, stroke grains of that material, and then we can completely understand the sampling properties of that ore. We must understand it at a number of different top sizes, and indeed, if we go back to this plot, of course, if we have sizes that differ, we could work at a 2 millimeter top size, and we would know what the top size of our gold was. We could work in here, so we can in fact interpolate here with great confidence, and we can use this sort of information to get a seriously solid design for our sampling protocol, where we have controlled all the sources of variance to give us a result that is fit for purpose. Here endeth the lesson. Questions?
That test with a very low grade gold sample, like around a gram.
Data of this nature is very scarce. But if you've got gram per ton type material and you've got coarse gold, follow the same sort of recipe and you'll get I'm absolutely certain you'll get the same sort of answer. This data that I used is absolutely like hen's teeth. It's totally unique. But I'm working with Rene to see if we can find some alternative ways to extract similar sort of heterogeneity information from the sort of numbers that come from using appropriate replicates in your sampling protocols.
How many more can we add to make how much more reliable? Is there validity in
Yeah, in fact, we really need to go down to a finer size that's going to get us towards the properties of our analytical aliquot. Because the analytical aliquot, the properties of that in terms of intrinsic heterogeneity, that's absolutely critical in terms of the repeatability of your fire assays. And if you find out that you can't get decent repeatability because it's very hard to break the gold, well, then you've got to go to leaching methods. Use larger samples. Your sampling constant is going to remain large. If it remains large, to get precision or accuracy, you have to use big samples. And that may mean that instead of using 50-gram fire assays, you've got to go to 1 kilo leach samples or 5 kilo leach samples and get your precision that way. Coarse gold, you know, people say 150 micron screen fire assays. 150 microns, too coarse. 75 microns is the way to go. So, you know, if you consider samples and then having to screen them at 75 microns and assay the oversize to extinction, that's a lot of work. Might as well leach the damn things and get an even better result because you can use much more mass.
Well, I think that's what Simon Dominic's been pushing for quite a while now, that for coarse ores you just leach it down to.
Yeah.
And that's why you should never, you know, do 30-gram fire assays on half an NQ core in these sort of ore bodies. So I think that much is known. But the question with regards to the sample nomogram that we've been sort of traditionally designing on, you know, variance equals K divided by M.
Yep.
With the three unknowns being your size, your mass, and your variance. With your formula, we're still constructing the same kind of.
Yeah, you if you want to have a nomogram, you can have it.
Yeah.
Because you're capable of calculating. I mean, you can just interpolate this thing as a function of size. So you can decide, you know, maybe I want to crush from 25 to 5 in my step instead of 3. You know, you can use this data. This number will interpolate nicely. That this plot is nice. It's behaving. So yeah, this is allowed to demonstrate that you can interpolate these figures. And indeed these figures. That's what it's saying. Exactly what it's saying. So yeah, you know, you get 3 or 4 points on for your material as a function of top size, and you're good to go. You're good to go to design sampling protocols that are going to contain the variance to a level that is, for you, fit for purpose. You know, and more accurate results, less risk. Less accurate results, more risk. So it's a trade-off. You know, how much are you prepared to pay for mitigating your risk? That means you got to convince the guy up the top, the accountants and all those guys. You got to convince them that this holds water, and they are the ones who are ultimately responsible for making those decisions. But you can go to them and say, yeah, well, this is the case, right? You know, this is how it is. Now you decide. And, you know, doing it properly in many cases doesn't cost a whole lot more than doing it badly. But you do it well because you know what you're doing. Whereas if you don't characterize materials properly, you don't know what you're doing. Simple as that. And this goes through to all sorts of different circumstances. And this is specifically for gold, but understanding sampling theory and material heterogeneity, be it a base metal ore or whatever, it's all the same in terms of knowing how to determine your optimal sampling protocols. And determine them early, characterize your material early, so that, first of all, poor procedures don't get ingrained, and second of all, you take advantage of having knowledge at an early stage and mitigating risk.
Yeah, that sample size on the top line there, that's the crush size of it.
There was material crushed to 25 mil, and there were 30 samples of a nominal mass of 273 grams.
When you analyse it though, what size do you get? stuff you analyse?
Oh, the analyze, this material would have been prepared extremely carefully in terms of how the heterogeneity of the material at subsequent stages of production. I mean, you can take each 273 gram at 25 mil, and you can
I think what you mean is it's actually been pulverized.
It's pulverized.
Yeah, it is pulverized. So everything, but what happens is you subtract an analytical variance later on from that variance at the top. So
I actually made allowance for a fire assay uncertainty.
Yeah, which Dick does as well in his paper.
Yeah, well, there's the allowance for analytical variance,
that's 4%.
and I took that out.
Yeah.
So this will work okay, so for instance at the grade, where we had low grade, and gold was small, pyrite, medium grade, it's larger, no, it's not pyrite. About 5 grams, it's free. Depending on where you are in your body, Jesus, you can have anything on that one there.
Yeah, well, you know, if you want to design a sampling protocol that is robust for all your ore, you take the worst case situation and you just live with it.
Well, domaining is still an issue. Right? I mean, up at the DPO, where they were doing the usual thing, low grade solid head pressure, and all this free gold came out and stuffed everything out. You would treat those things differently. You would have, I mean, they sample through that with the same sampling protocols. Nothing changed initially. But if your variance goes through the roof because of all this on coarse gold, you need to increase your sample mass.
This mob in WA that makes this tumbling rig, that's the Leachwell stuff. It's they call themselves mineral control something or other.
But that's really, well, if it's that coarse, then you've got to do something else, or you just need a really light sample and a light subsample. But that's what this nomogram is supposed to do. How large does the sample need to be at every stage to limit your variance that you introduce? You know all this, obviously, but so if I see
that examples of pure gold, but you also your mineralisation, you can actually drill into one sample. It's very, you've got to capture that as well.
Yeah. And look, I did this test because I did this. I used the same paper, the same procedure, and then went on to Masbate, and they gave me 0.6 gram ton material, which I was told was going to be more than 10 grams per ton. Worst case scenario, as you just said. Obviously, the 0.6 gave beautiful results and gave small sample requirements, but if that's what you base your sampling on, if it's not actually representative for your actual ore body, then you're sort of lost. So if you got standard, you got sort of 1 gram per ton stuff, and you can actually then lay it out, then I would probably have a sampling protocol for that. But if you never know, then it's worst case scenario.
Yeah, but if you got low grade and coarse gold, then it gets really bad.
Yeah.
And the only solution, even at the low grade, the only solution is big samples and leaching. Any more questions?
Some more beer left. So yeah, thanks, Geoff. It's excellent. So.
Thank you.